Welcome again, or still, for those of you who have not left the room yet, thank you for sticking with us. Peter Cooper and I will be presenting this piece of content on behalf of Intel. The good people from Intel have not been able to be here, to attend here in Prague. But the content is very important to the Immersion community as well. We'll go into that. The slides that we're going to be taking you through have been prepared by Jessica Goldbrandt. She is the vice chair to the incubation committee within OCP as well. And she's been a very steady contributor involved closely with the leadership in the Immersion community as well. And let me just get this kicked off. In December, Intel has contributed the immersion fluid specification. This specification is fundamental to the industry and for the adoption and scaling of immersion cooling. And there's a very simple reason for this, because the fluid is actually central in an immersion deployment. It's central to the core function of the IT equipment, which is immersed in a solution. And it is responsible for the protection of the IT equipment, right? The fluid touches everything. All the materials that are embedded on a motherboard or in a server are touched by these fluids. The interoperability of these components is therefore dependent on a very close coordination between a lot of stakeholders. We're looking at CPUs and GPUs, the server equipment manufacturers, and the component manufacturers. To enable this collaboration, Intel has defined a solid baseline to which all these manufacturers can test and evaluate their materials and equipment. The fluid specification is therefore the first step of a process to determine what is required by the immersion fluid to meet the IT equipment performance needs, which are current and future, right? So we are talking about various applications that already exist, but we have to be ready for tomorrow as well. The goal of Intel behind this specification is to enable this larger ecosystem by aligning on the immersion fluids meeting IT equipment needs. And this is done by ensuring that chips, but also the products of other OEMs, other chip manufacturers, and other stakeholders like tank manufacturers are fully aligned and working with the same basis. And this is made possible by utilizing the collaborative approach within Open Compute, which enables a strategic approach to facilitating full platform support within immersion cooling. Right? It's something that we all strive towards. And the fluid spec has been published, and it covers in-depth thermal performance criteria which all fluids must meet. It also includes important references for signal integrity evaluation, which is going to be covered in the next session after this. And de Jong is going to speak to this. But the Intel Fluid spec also addresses a lot of sustainability aspects towards the fluids. It closely relates to another piece of work which has already been published as well in the same period, end of last year, which is the material compatibility for immersion paper. It goes into all the wetted materials within a piece of IT equipment and the appropriate test and evaluation methods and approaches for compatibility within immersion fluids. And this is something that has been presented in the opening session, will be further worked on in the upcoming year, right? So that's going to be expanded on. Intel has committed and is deeply involved now in that work stream. for facilitating this expansion of the current materials that we have. And with these work products in hand, the industry can start with standardized test methods and approaches for compatibility of materials. These test methods and these type of evaluations can be performed by fluid manufacturers or vendors, component manufacturers, independent labs, or even immersion solution providers, right? Any potential incompatibilities or simply just enhancements to the design of a system to improve its performance, to address some of the additional performance potential which comes with immersion, can be addressed with these test methods and can be addressed in this process. And that will facilitate further thermal performance optimization and overall reliability testing with a goal to facilitate fully qualified and warranted products in immersion. And to enable all this, the fluid specification is dealing with a large variety of fluid properties. Some examples are here on this slide. All of these properties have been dealt with and they have been harmonized with the broader community. Right? We spend a lot of time with the community going into the details about, hey, what is viable? Is this appropriate? What are the pros and cons? Which values are correlated with each other? And one of the main challenges which quickly became obvious is that a lot of these properties can be wildly different for these different types of fluid, right? Whether we're looking at hydrocarbons or esters, fluorocarbons or anything else, right? These values can be all over the place for different types of fluids. The fluid spec quantifies all these values and assigns very specific minimum or maximum values to ensure a predictable behavior towards IT performance in immersion. We're getting into, and some of this is captured in stuff like figure of merit. Now, I'm not a subject matter expert on these kind of things, which is why I've enlisted the help of Peter Cooper, the new co-lead for the fluids and materials, to help with explaining to you what the relevance is of these figures. So, Peter, please go ahead and help me out here.
Thanks, Rolf. So yeah, what are the critical properties of fluids? I'm going to talk about two of the most critical properties, I think, here, which really go to the heart of what dielectric fluids in this application are doing. They're removing heat and they're dielectric, right? So in terms of the first thing, removing heat, we've had this problem for a while now where if you want to try and assess how well a fluid removes heat, you open up a typical product data sheet of a fluid and you'll see a number of properties which affect that, but especially density, viscosity, thermal conductivity, and specific heat. And if you just take any one of those, you can't really come up with that proper assessment of how it removes the heat because it's a combination of those properties. So, you know, people might ask, what's the maximum viscosity that you can have? Well, that would depend on what you want to cool, but it also depends on those other three properties, right? So Intel's strategy here is to define figures of merit which capture that combination of properties. There are several figures of merit which are based on the particular technologies of immersion, right? So I'll just run you through briefly some of those figures of merit. So starting here, we're looking at single-phase fluids. There are two figures of merit, one based on natural convection and the other based on forced convection. The way they derive these expressions, you can see on the slide here, are from simplified models of each of those ways of transferring heat, right? And to come up with some guidelines of what people should be targeting within the spec, what Intel have done is taken a look at all the fluids available on the market today, or a significant number of them. They've analyzed them as per these equations here. And then they've also done experiments on their chips to try and come up with some initial limits, cutoff limits, in terms of these figures of merit. So In terms of figure of merit 1, natural convection, there are actually two cutoff limits that were defined. One is performance optimized, which is greater than 45. The other is a cost optimized solution greater than 35. To put that into context, Intel in their document, they explain the 35, greater than 35 can, in most cases, cool a third generation Xeon CPU within a single U. When you get up to the 45, that's where you get to fourth generation and potentially beyond. In the future, they have highlighted that they might have to introduce further tiers of figure of merit 1. The second figure of merit is based on forced convection, and here it's greater than 19. I did just, sorry, Rolf, just wanted to quickly show. So on the right, you can see some graphs of the figures of merit with respect to these fluids with the cutoff limits. Really important to note is if you look at the fluids on the market today, both fluorochemicals, hydrocarbons, and others, there are a significant number of fluids that don't meet that cost optimized solution and many that don't meet the performance optimized solution in figure of merit 1. So kind of throwing out the challenge there for future development. Here, figure of merit 3, that's based on laminar flow in a pipe, right? They've also done some derivations from simplified models of laminar flow. What that boils down to, though, is the dynamic viscosity when you remove the dimensional factors. Again, they've based that on less than 1.5 times 10 to the minus 2 Newton second per meter squared, or pascals. And here again, if you look at the cutoff limit, you can see that there are some fluids on the market today that don't meet that threshold there. Finally, in terms of figures of merit, two-phase fluids, here they established figure of merit 4 based on the critical heat flux correlation that was put out there by Zuber. Simplification of that, they came up with figure of merit 4. Cutoff for that is 1.1 times 10 to the 6. Looking at the fluids they analyzed in the graph here, they all met that criteria. What they did note was more than differentiation in terms of figure of merit 4 for two-phase fluids. You're probably going to be looking at things like boiling point, material compatibility, and reliability. So beyond the thermal properties, the other aspect was dielectric properties. And here you can see the table of dielectric properties. Starting with dielectric strength, this is where the input from the immersion requirements workstream was really important. This is directly from the specification that was developed there, greater than 6 kilovolts per millimeter gap. There was a lot of input from the community around that. What wasn't so clear before they developed this spec were the dielectric constant, dielectric loss tangent values. So Intel again did some experiments looking at much higher frequencies that had been considered previously and came up with these limits for dielectric constant less than or equal to 2.3 and the dielectric loss tangent less than or equal to 0.05. And Andy, I think, will touch on that later in the signal integrity talk about why that's important. Volume resistivity, that's another value that came from the immersion requirements document. So with that in mind, I'm going to throw back over to Rolf to show the full spec and talk about how you can access that.
Thanks. So, yeah, you can access this spec by scanning the QR code. The link is also on the Wikipedia. We are running out of time now. But yeah, as you can see, here is a specification table for the explicit requirements towards meeting this specification. I need to highlight here that this is a base specification which provides a basic design outline of what an immersion fluid should meet. It doesn't prescribe the actual fluid chemical consistency or the chemical properties of the fluid itself. This can be applied to a large variety of fluid types, whether it's esters, hydrocarbons, or fluorocarbon fluids, single phase, two phase. It's completely irrelevant. This can be applied to any kind of immersion fluid. So this fluid specification is a result of a lot of work primarily done initially within Intel, And after that, we spent, I think it was about 5 or 6 months with the community to harmonize the explicit details that had gone through extensive further modifications with all the knowledge and experience that the community has brought to the table to optimize this base specification. A lot of this information is now also crossed over to the immersion requirements, not with the explicit values, but with a disclosure requirement for additional parameters of specific fluid. That's something I will touch upon in the last presentation for this morning. So that's still on the agenda for later this morning. So far, we're out of time. I want to thank you for the attention, and thanks Peter for helping out on behalf of Intel as well. Again, call to action, we need your help. If you have knowledge and experience on these topics, please do join the communities. The materials and fluids community is mostly involved with the specification. And with that, I would like to end this presentation and make space for the next one. Thank you very much. Thank you.